In this AWR TV video, we're going to take a look at a new feature in version 2010 of the AWR design environment. And this feature allows us to take measurements for amplifiers while holding the output power constant. This is a great new feature for those of you who design amplifiers, especially if you want to look at the nonlinear characteristics of amplifiers. Now, the example we're going to use is one that's right out of the box. It's the high power BJT amplifier example, and it's been around in the tool for quite a while. It's one of my favorites because it does let us exercise so many different aspects of microwave office and allows us to learn so many different things about not only how to use microwave office, but some insights into electrical engineering as well. So I love coming back to this example time and time again. What we have here is the bipolar amplifier that we're just showing in its basic schematic form, but it's going to be embedded into some test benches. And when we embed it into the traditional test bench to get power and efficiency, we'd normally get a plot that looks something like this. So we're going to sweep the output power, we're going to sweep the input power, we're going to hold the frequency constant, and as you can see here that we can see that the output power is going to change. As we do that, it's going to come up naturally, and because we're looking at the nonlinear characteristics of the amplifier, you can see that this is not a straight line. So the gain and the power out does change as a function of the input power, which is a hallmark of nonlinear behavior. Additionally, you can also see that the DC to RF efficiency, the power added efficiency, is changing, and our DC to RF characteristics is changing. So we're obviously in a highly nonlinear regime of this amplifier. And this is all fine and good for fixed frequency, but oftentimes we want to hold the output power constant and see what we need to do over frequency to make that happen. So the way we do that now in version 2010 of the AWR design environment is for the single tone case. We'll take a look at it here, and then we'll go to the two-tone case. Is we have this new control block called const p out, and what this basically does is send a directive to the harmonic balance simulator, the AppLac engine, and it specifies that we want to hold the output power constant at 38 dBm, and we want to look at an input port of port P1, and we want to look at the output port of port P2 over here, and we're going to attempt to control through the simulator directive. We want to hold that output power at 38 dBm as measured at port 2 here by varying the power at port 1 here as we're sweeping the frequency, so we can look at some of the frequency related characteristics while doing that. We specify what sort of measurement we want to take. Is it a function of the harmonics that are presented in terms of the simulation, so the tonal harmonics of our sources? As an alternative, we can also have it specify the a band. We can look at some sort of a range of frequencies that we want to look at as well, and we give it an error function because it's going to try to iterate the input power to hold that output power constant, and we tell it what sort of function, what sort of measurement we're going to look at the output. In this case, we're just going to look at the frequencies associated with the input tone, or tone 1. And when we do that here at on our curve here for our that's for our two-tone, we'll come back to that in a second. If we go back to our single tone measurement, here we go. You can see that our output power is in fact being held constant as we're sweeping the input frequency from 150 megahertz to 250 megahertz. And in order to do that, in order to make that happen, the simulator is varying the input power, shown here in blue, to get that output power to be constant. Now, simultaneously with that, we're also measuring the power added efficiency, and you can see that as we sweep the input frequency to hold that output power constant, we're losing quite a bit of efficiency. So this amplifier is clearly operating in a highly nonlinear fashion. Now, to do this for the same sort of measurement for a two-tone, if we're interested in intermodulation distortion, we use the very same constant P out block, and this time we're going to specify as the frequency function that we're going to look at, it's going to be both a function of the single tone and the two-tone, or the offset in this case, because we're going to use a port delta definition for our two-tone as I'm showing here. But basically we're taking the very same measurement. We're going to hold constant at 38 dBm. We're going to vary the power at port 1, measure that 38 dBm at port 2, and we're going to look at a function of the harmonics. And when we do that for our measurement here we go, we can look at the two-tone output power, and you can see that while holding the total power out, our intermodulation distortion is changing as we go across that 150 to 250 megahertz sweep input frequency. So this is a great new feature for power amplifier designers when you really want to look at some nonlinear characteristics of your amplifier that go beyond the very simple sort of measurements where we're going to sweep the input power or we're going to sweep the input frequency. This is the ability to actually direct the solver to hold the output power constant while sweeping both input frequency and input power. If you'd like to play around with this example, as I mentioned, this comes with the software, so it's right out of the box. You can go to the AWR website and download a free demo of the complete Microwave Office design suite with this example. And if you'd like more information about this, there's other AWR TV examples, there's white papers on the AWR website, or as always, you can contact your AWR sales professional.